John. I'll just bring up my slides. Okay, I hope you can see that. Shout if not. So I'm Jamie Holder from the University of Delaware. Thanks for the invitation to speak here, and thanks to John for organising the meeting. It's a really interesting programme. And I'm reporting on the work we've been doing with VERITAS in coordination with Breakthrough Listen. And this is on behalf of myself and a grad student, Greg Foote at the University of Delaware, and also David Williams and his student Nico Vasquez at UC Santa Cruz. So, fortunately, Paul has already given a wonderful summary of the history and the motivation for pulsed optical SETI. So I don't need to go through that, except just to remind you that the numbers tell us, if you look in Howard et al., that a laser pulse from a nearby star system is fairly easily detectable here at the Earth. In order to detect it, you need ideally large light collectors. But a point that I would stress is that they don't necessarily have to be very high quality. A light bucket is sufficient. You also need fast photon detectors so that you can record this nanosecond pulsed signal. Unfortunately, we already have devices that have both of these properties. These are atmospheric Cherenkov telescopes. These already exist. They've existed since the 1960s. They're the largest optical telescopes in the world and have been for 50 years. And they have these same requirements, large light collectors and fast photon detectors. So the idea of using these for optical SETI has been around for some time. It was mentioned, I think, back in 2001 with regards to STACY. And then we looked at it with the Whipple 10-meter, and then STACY subsequently published some limits on a search for optical SETI pulses from nearby stars back in 2009. So this has been around for a while. The basic idea is fairly straightforward, illustrated in these pictures here. This is, on the left, you see what we built these telescopes to do. They're designed to detect Cherenkov light from particle cascades which occur in the atmosphere, maximizing at about 10 kilometers altitude. And if you detect the light produced by these particles in the atmosphere, then the images look something like shown in these gray field of views here. You will be able to record an image of the shower. If your telescopes are viewing the shower from different positions on the ground, then they will see the shower appear at a different position in their field of view, and it may have a different intensity and a different structure. Conversely, if you look at a distant laser pulse with all of the light arriving in parallel, if you view this from different places on the ground, it will simply look like a point source with the same size and shape as your optical point spread function, and it will appear in exactly the same place in the field of view of all of the telescopes. So we can use this both to detect these pulses and to discriminate them against the significant background due to these particle cascades in the atmosphere. So we decided to try doing this with VERITAS. The VERITAS telescopes are shown here. We have 4 of them. They're 12-meter diameter mirrors, so you can see cars and shipping containers to give you some idea of the scale. These telescopes are separated in order to give us different views of the particle air showers. They're separated by about 100 meters from each other. So this parallax effect should be pretty clear. And this is in southern Arizona, halfway between Tucson and the Mexican border. Here's one of the telescopes on the left here. You can see me for scale. I'm a fairly average sized human being. Each of the telescopes has a diameter of 12 meters. So we have 110 square meters of mirror area. And up at the focus here, up at the camera, we have an array of photomultiplier tubes, giving a total 3.5 degree diameter field of view. We don't read out all of the time. An image has to be, a readout has to be triggered. And for the telescopes to be triggered and read out, we require a coincidence between at least 2 of the 4 telescopes in the array, and this coincidence has to occur within 50 nanoseconds. And if we trigger, we then read out an image of, using the camera with 2 nanosecond sampling flash ADCs. So this is what our background data look like. These are cosmic ray images, and because we're reading out 32 nanoseconds with 2 nanosecond sampling, we can actually take little movies of these particle cascades in the atmosphere. This gives the moon to give you the scale. These are 3.5 degree diameter, and you can see these are fairly large, highly structured events covering sometimes many degrees across the field of view, and appearing in different spots in the camera due to this parallax effect. Okay, so optical SETI pulses will, as I've said, look different. This shows you a small cosmic ray event where the light is relatively compact and covering a small part of the field of view, but it appears in a different place in different telescopes. So we could exclude this as an optical SETI event because of that parallax effect. On the right here, you see an event that does appear to be similar to what we would expect for an optical SETI event. Small pulses about the same size as our optical point spread function in the same place in all 4 telescopes. However, in this case, the pulse doesn't arrive from the target that we were studying, in this case KIC 846-2852, Boyajian star. And furthermore, if we just look at a few events before and after this event, we can see that they track across the field. So this was clearly not an optical SETI event. It was probably a satellite, given the speed at which it was moving. So by studying these images, as seen in multiple telescopes, we're able to achieve really efficient rejection of both cosmic ray background events and other spurious background events. So this was the idea that we applied to some observations of Boyajian star, one of the first to be identified as a candidate for the transiting megastructures that Anne-Marie spoke about. We actually didn't even need to take any new observations to do this analysis. We had 10 hours in the archive already. So we analyzed this, searching for optical SETI-like pulses, and we published this in an AppJ letter back in 2016. The technique seemed to work. Unfortunately, we didn't see any pulses, but the technique works very well. Over the full field of view, only 1 in 250,000 triggered events were retained, and none of them came from the location of our target. This allows us to estimate our sensitivity, which comes out to be about 1 photon per meter squared per pulse, which is the most sensitive optical SETI device. And this is a fairly conservative estimate. This 1 photon per meter squared per pulse corresponds to about 20 photoelectrons, which is a pretty easily detectable signal in our telescopes. As a result of this paper, we started collaborating with Breakthrough Listen. And since 2016, we've coordinated some observations and received some support from Breakthrough to help with this. And we've so far collected 50 hours of observations of Breakthrough Listen targets. And we've also started searching back in our archive for pulses from breakthrough listen targets. And we have 12,000 hours in the VERITAS archive of observations. These first results are in prep. Greg Foote, my grad student, is showing them at the AAS meeting this summer, and we'll have a paper out on those soon. And this will contain 30 hours of these dedicated observations from 2019 and 2020, plus an analysis of 200 hours of archival data. And this shows all of the breakthrough targets, which will be summarized in that paper. Looking forward, in principle, if we analyze the entire VERITAS archive, this would allow us to survey 20% of the celestial sphere. So this is not taking any new observations. This is simply going back and analyzing our archive. So this balances the fact that we have a fairly small field of view, a 10 square degree field of view. Fortunately, VERITAS has been running for 15 years, and over that time, we've surveyed an enormous chunk of the sky. So really, we just need to process these data, to perhaps refine the analysis algorithms a little, but it's essentially a question of manpower and computing power. There's no reason not to do this. In developing this optical SETI with Cherenkov telescopes, there's a few considerations that come along if we were to consider doing this with next generation instruments. And I thought it might be useful just to list those here. In particular, the number of telescopes and the telescope spacing. So having 4 telescopes is extremely powerful. It's very difficult to fake a signal if you require it to be in the same position in the field of view in all 4 telescopes. The telescope spacing is critical, so that you can discriminate using this parallax effect. But VERITAS is not ideal for this. Ideally, you would separate your telescopes by more than the size of the Cherenkov light pool on the ground, or even place telescopes at different observatory sites. The ratio of your imaging pixel size to the size of your optical point spread function is important. And then one of the critical and probably the most challenging things for future projects is designing a system that is able to trigger on a single pixel on a nanosecond pulsed point source. So yeah, we would like a single pixel trigger, and ideally with a hardware coincidence between widely separated telescopes. And CTA, for example, is not really designed to do this. So this is a consideration for going forward. The field of view, of course, is important. The larger your field of view, the more sky you can survey more quickly. And pixelation is also important. The imaging that we have with VERITAS already really helps provide some of that context that Paul mentioned, where you can, if you can see what is going on around the region where the pulse may be coming from, you can tell more easily if it's really has the characteristics of an optical SETI pulse. And then, of course, big mirrors and sensitive photon detectors. So my ideal instrument would be something like the SETI telescope, which we're developing as a prototype at VERITAS. This has 11,000 pixels with an 8-degree field of view. And I would ideally have a few of these separated by 500 meters. Okay, so let me finish with a summary. Cherenkov telescope arrays are really extremely sensitive instruments for optical SETI. VERITAS is already working as a world-class peer-reviewed optical SETI observatory. And this is in part due to this pilot program, which we're running with Breakthrough Listen. There are simple ways that we could achieve order of magnitude improvements in the future. Simply analyzing the VERITAS archive would give us order of magnitude improvements in the amount of sky that we've observed. As Howard mentioned, we're coordinating some observations soon with VERITAS and the Automated Planet Finder at LIC, which is a fun new project. If anyone else would like to take part in these observations or to set up something similar for the future, please send me an email and we'd be happy to look into it. And I'll stop there.
Thank you, Jamie. So let's now open the floor for question and answers. I'll start with the question from Tan Sudelan. So what are the assumptions on the duty cycle of the pulses in these searches? So is it marginalized over the reported lifetime?
Yeah, I see it. That really comes down to the hardware of the telescope and what duration of pulses you're able to trigger on, which basically comes down to the properties of the preamplifier that we put at the back of the photomultiplier tube. So I think I did a calculation once, and we would be able to trigger on pulses with rise times as long as maybe 100 nanoseconds. But longer than that, we because our signals are AC coupled, then we're not able to trigger on pulses that rise much more slowly than that. I can give more details in the chat later if that didn't address the question. Do I have time to look at the other questions, John, or do we need to go to break?
Let's just go with one more question, and we are heading for the break.
Okay, I see Dan's question regarding the satellite you showed. Does the brightness need to fluctuate on nanosecond? That's a good question. I think the reason this satellite, so most satellites don't trigger. A faint satellite traveling through our field of view won't trigger. I think the reason this satellite triggered is that it's quite bright, and that causes just an increased Poisson fluctuations in the pixels that the satellite was included in, and we see this with bright stars as well. So your probability of getting a random accidental coincidence goes up simply because your optical background is fluctuating so much more. Yeah, the satellite wasn't pulsing. I hope one of our later speakers from Tiger will tell us about, well, actually, I don't want to give any spoilers, so I won't mention that.
Okay, thanks. So I also see Shelley and Albert for question. Perhaps we can take it offline with Jamie, so to have a private chat or email correspondence. So thanks everybody for attending the first session. So let's now have a break for 10 minutes, and we will reconvene at 10:10.